Awesome. So let's just go over a little bit of what we did yesterday, or not yesterday, last Friday. Uh, what we really did was define this flux through an outward flux. Sorry, that should be outward flux through a surface. Um, no, I guess that should have been flow based on the sentence. Sorry about that. Mondays. Um, so we described this flux through a surface, and it's really kind of the same interior integrand, this f dot n. In this case, our n is defined a little bit differently. So here's our surface. Our n is this outward vector here. And we get this from taking the cross product of the two partial derivatives of the parameterization of our surface. So once we put all of this together, we parameterize S, we write out everything in terms of U and V, we get this nice formula down here. Again, this could probably be written a little bit better as F dotted with this cross product vector, but this is the idea. So we went through at least one example of this, talked about moments with mass, thin shells, which is the surface. You can go through and compute those. And that took up pretty much all of Friday. We also talked about what order you should take these cross products in, and take them in kind of the forward direction order, I'd say. So meaning x and then y, xz, yz. That should be the order of the cross product here. And then we talked about what's coming forward. So what are we going to be doing today, tomorrow, Wednesday? Fridays, I think is going to be mostly review, but I think the rest of this will bleed into Wednesday. So 16.7 is Stokes' theorem, 16.8 is the divergence theorem. And the schedule has it a bit backwards from how I'm going to cover it. I'm going to cover it with with Stokes' theorem first and then divergence theorem. And to just give you an idea of what these things are, what these theorems are, we can look back at Green's theorem, which is two-dimensional circulation or two-dimensional, oh, I can't think of it, flow or work, there it is, computation. So it's this integral, it relates a work integral to a surface integral, or sorry, to a double integral over a region in the xy plane. So this is all 2D in the xy plane. And this formula looks a little bit weird, but it's actually correct. So for Stokes' theorem, again, it relates circulation, but now you have a curve in 3 dimensions that forms a loop. And that loop forms a boundary, forms the boundary of a surface out in 3 dimensions. So in Green's theorem, this is all 2D xy plane. Stokes' theorem, it's the same exact idea, except this is now in 3 dimensions. Same sort of thing with the divergence theorem. 2-dimensional Green's theorem says in the xy plane, we have this flux for a loop, can be related to a double integral over that region. Whereas if you want to look at flux over a surface, which is closed, so it has a boundary curve is what this circle is supposed to mean. Or sorry, not a boundary curve. It has it forms the boundary of a 3-dimensional object, right? Just like the curve forms the boundary of a surface, something like this. The surface forms the boundary of a 3-dimensional volume. So either way, you can set up a surface integral, which we've found is a bit of a pain, or you could set up a triple integral, which we've done a lot of. So honestly, computational wise, divergence theorem is a lot nicer. Sorry, the flux theorems, I should say, because we trade a curve for a double integral, we trade a surface for a triple integral. On the right side, we don't have to parameterize anything, so that's kind of the nice thing about that. For circulation, unfortunately, in Stokes' theorem, you always are going to have to parameterize something. So it's kind of whatever the problem asks you to do, or whatever the if one is actually nicer than the other, I don't know. Parameterizing surfaces and curves, they're kind of the same. So that's the overview. That's what's basically going on. And let me, sorry, clear this page from office hour stuff. But in the meantime, are there any questions about anything? I saw this morning that the discussion boards were pretty busy. There were a lot of people posting. I didn't get a chance to actually look at them, so hopefully good things were going on there. Yeah, what is the Nabla and the Stokes? What is this vector? So we're gonna get into that. But I guess since we asked, we actually saw this a little bit earlier. This is equal to just the vector of like partials, not partial derivatives, but just partials. Right, I think we saw this with the gradient. Right, I said gradient is, gradient of f like this, where if you take f and you kind of distribute it to each of those, you get the partial derivatives of f. And so the same kind of thing applies to each of these parts. Right, you're taking a cross product, so these better be three-dimensional vectors. You're taking the dot product, so f is a vector field in 3 dimensions. Usually, like here, you need to write it as, kind of xy0 as your vector field. So it's weird that you kind of have to think in 3D about that, but it's not too bad. So like I said, we're going to do Stokes' theorem first. This is the longer of the two sections. So here's the theorem. Let S be a piecewise smooth oriented surface with piecewise smooth boundary curve C. So you can think of this as kind of like a dome or like a half sphere. Right, you could think about it something like this, where this boundary curve, this open circle here, this is C, where the surface is the rest of it, including that. So that's kind of the picture, like maybe you want to have in your head. or like we had before with that sort of curved wall, the square, or like the boundary of it, right? The top, um, kind of the curved top and bottom, and then the left and the right sides. Like that would be the piecewise boundary curve. And each piece is smooth in that case, right? That's what we want. So this is the setup. We want to let F be our vector field, and again, we'll just take M, N, and P, be that vector field. I'm just going to say nice components. What this nice will mean, I'll say it in words, have continuous first partial derivatives on, basically the surface, right? But don't want to write that out. It's everything that we would want these components to be, everything that we would want these functions to be. So they're nice. Then, if we have all of that, circulation of F around C in the direction counterclockwise with respect to the surface's unit normal vector n. So, okay, this is the circulation with all of this equals the integral of this quantity, which we will now define as the curl of F. Take that vector, dot it with n. So it's the integral of that quantity over S. Right. So this is what it would be written out in words, and this is a little bit, I think, this is still useful to write this all out because of this part right here. Right, the direction counterclockwise with respect to the surface's unit normal vector. So depending on what you assign to be the unit normal vector, you want to take the counterclockwise direction with respect to that. Or if you pick a counterclockwise direction, that forces you to pick, an appropriate normal vector. So let me write this out. Circulation is equal to line integral f dot dr is equal to a surface integral curl of f dot n d sigma. So coming back up to the picture up here, sorry, maybe I'll wait a second just so we can write this down. Or better yet, I'll redraw the picture. So here's kind of our dome with boundary curve. So the idea is if I pick this direction, kind of going this way, to be my counterclockwise direction, that's a d sigma, sorry. So let's see here. Right, there's two kind of counterclockwises. It's whether you're looking at this thing from the top down or the bottom up, right? If you look at it from the top down, then this direction, like we had before, is counterclockwise. Whereas if you look at it from the bottom up, you have the other direction being counterclockwise. So if we have a normal vector going this way, so I might go back on this. I don't think so though. If we have a normal vector pointing up this way, that means we want to look at this surface from the top down. So we want to look at it as if this normal vector was pointing towards us. So if this is the case, then we take this direction to be counterclockwise. However, if we had our normal vector kind of pointing on the inside, so we want to be looking at this from the bottom up in this case, then we want to take this direction to be counterclockwise. So basically you want to be standing wherever the normal vector is, or the normal vector is pointing. So let's do an example and kind of check this out. Let S be a hemisphere, just like we drew above. Or I should say let S be the hemisphere, which is given by x squared plus y squared plus z squared is equal to 9. But with z being positive, right? So it's the upper hemisphere of radius 3 in this case. C is the boundary of S. So if we're looking at this and we're thinking about it, C should be where z equals 0 meets this hemisphere. Right, so C should be given by this circle in the XY plane. Let F equal y comma negative x comma 0. And we want to check that Stokes' theorem holds. So we're going to compute both sides of this. Okay, so for part A, we're just going to check the left side. So we're going to parameterize this curve in a counterclockwise direction. Then part B, we're going to check the surface side of this. Okay. So like I said, we need to first parameterize C. Our boundary curve, if we were to draw it out in the XY plane, in this case, it's nice because it's in the XY plane. Right, it's going to be a sorry, a circle of radius 3. And if we pick a counterclockwise direction for this, then that's kind of telling us where our normal vector should be. So again, if we pick counterclockwise, that's like going back up to this hemisphere and picking this outside direction, right? This pointing up direction. Let's draw out the whole three-dimensional picture just to get an idea of that too. Right, so this is a sphere of radius 3 cut off at the xy plane. So we'll try to draw this thing accurately. Sometimes this doesn't turn out very well. Oh, sorry. I wanted that to be the boundary curve. So we have that. Oops. Great. So I drew that where the pink or the red here is the boundary curve, but here's our half dome. Here's our hemisphere. So right, if we pick this direction to be counterclockwise, which is the same thing as this direction, and we're picking our normal vector to be pointing outwards. And again, this normal vector will come into play later. Okay, so to parameterize t, not that big of a deal. We've done this before. It's a circle, so we can use polar coordinates. So to change from x and y to r and theta, we change it to a 3 cosine of t, or theta if you're not using t, comma 3 sine of t, comma 0. Right, in our integral, we actually, in this integral, do we need to be 3 dimensions? We probably should, since our vector field was given in 3 dimensions. Even though there's a 0 in our z component for the vector field, we still probably should write out our parameterization of this curve in 3 dimensions, since that's kind of what Stokes' theorem is telling us about. You know, it just so happens in this example that we are setting the z component equal to 0 in both cases. Anyways, there's our parameterization of the curve. Now we need to write out our vector field in terms of this parameterization. So we have positive 3 sine, comma negative 3 cosine, 0. Then we need dr dt. We get a negative 3 sine, three cosine, 0. We're missing one thing. Sorry about that. Missing our bounds for t, and of, you know, this is a circle, so it's going to go from 0 to 2 pi. So altogether, our circulation is going to be 0 to 2 pi of f dot dr. It's actually a really nice integral. So if you dot these together, you get a 3, well, let's not skip any steps here, at least for this part. You get 3 sine -3 cosine 0 dotted with -3 sine 3 cosine 0 dt. So when we dot these together, remember it's the product of the first 2 components plus product of the second 2 components plus product of the third 2 components. So altogether you get a -3 sine squared minus a 3 cosine squared plus 0. But we can factor out this -3. We get a sine squared plus cosine squared. This turns into a 1. So altogether, this is an integral of 0 to 2 pi of -3 dt, which we can go through and compute. Not that bad. In this case, you should get a -6 pi. Okay, so we've done a bunch of these types of integrals, but I'll pause here just to see if there's any questions. Shouldn't it be -9? Yes, it should be -9. And I got a little too carried away with going fast, so sorry about that. You were absolutely right. What's 9 times 2? -18. If I check my key, yes, or my my notes, yeah, that's what you get. Thank you. Are there are there any other questions or remarks about this? Great, not seeing anything. So this is the line integral side. Now we want to double check that circulation is equal to also this surface integral. And so the first time we actually are computing curl. Okay, but before we go through and compute any of this curl or normal vector stuff, let's parameterize S. Right, so let's remember S is the hemisphere. So it's given by these equations. Well, it's a hemisphere, so kind of the best coordinates we can use should be spherical coordinates in this case. So let's scroll back down. Let's say R of blank blank is equal to X, Y, Z. I skipped this with parameterizing the curve earlier. Sorry about that, probably should have gone a bit slower. But the idea is that, again, we want to change X, Y, Z into rho, sine, and phi. If we're using spherical coordinates, a sphere or this sphere can also be described as rho is equal to 3. So taking the shortcut, we actually get 3 sine of phi cosine of theta for X, 3 sine of phi sine of theta for Y, and 3 cosine of phi for Z. Remember, these are our substitutions. Instead of the 3, you would have a rho in general. But the idea is now we have phi theta as our variables. I'm going to go somewhat quickly through the partial derivatives because they are just partial derivatives. 3 cosine phi cosine theta, 3 cosine phi sine theta, -3 sine of phi. R sub theta is -3 sine phi sine theta. Y is +3 still. Cosine phi cosine theta, and 0 for the third component. Again, you might be like wondering, like, how do we know it's exactly this cross product? You know, I kind of asserted earlier, take them to be in this order, and like things will work out. Right, so this is a hemisphere in the top half of the well, actually, it really doesn't matter if this is a hemisphere in the top half of the bottom half here. But this is kind of on the outside of the surface, right? This is where did I draw it? Right, our normal vector is pointing on the outside. Our curve is actually in the like honest clockwise direction if you were to draw it in the XY plane. Right? As long as you do these type of things, then you don't have to really worry about the order of your cross product of these partial derivatives. Everything will work out. So if we do this, and I think even if you try to go write these two variables out, or if you take your hemisphere and like write it in the phi theta plane, which that reminds me, we need to write out bounds for this surface. Theta, that's the easy one, 0 to 2 pi. Phi, that's a slightly more interesting one. So remember, the angle phi goes from pointing straight up to kind of falling down until it points straight down. Right? It has this type of, or I'll hold it sideways, it has this type of angle. So if it points straight up, and then the hemisphere, it goes until we're pointing sideways, this would be an angle of pi over 2. So phi goes from 0 to pi over 2. So I think even if you were to kind of flatten this thing out into a phi theta plane, I think you also might see that you know, the normal vector coincides with this counterclockwise direction. Anyways, we're not doing that today. I'm also not going to go through the entire cross product here, but I will simplify it a little bit. So you get a 9 sine squared phi cosine theta, comma 9 sine squared phi sine of theta, and you get a 9 sine of phi sine of theta, sine of phi cosine of phi. So that's what you get for the cross product. I'm not going to go over it. It's a lot of multiplication. It's a little bit of simplification. But here is the kind of brand new interesting thing. The curl vector. Right? We describe this as nabla cross why is the second component of r theta not 3? Because no matter what things we're multiplying here, we're always going to get 9. Right? Because we're going to get the 3 times 3, which is what I messed up earlier. Right? So second component is this 0 with a bunch of negatives out in front of this other term. No, the sign part. Sorry, this part? I'm confused. Did I write something down wrong?
Can you hear me?
Yeah.
And the second component of r theta, when it says 3 cosine phi? Why isn't it 3 sine phi?
Oh, I'm sorry. Yes. Sorry. That was my fault. I didn't read your comment correctly. Yes. Reading comprehension is good for everyone. Yes, that should be a sine phi. Sorry.
Thank you.
Yeah, I have it written down in my notes, but again, that's kind of the case of trying to go too quick. What are we doing? Curl vector. Right. So it's curl vector is nabla cross product with our vector field. And I'm going to write this out in its details because this is kind of the first time we're going over this. So this is an odd thing where we don't want to substitute in our u and v variables, at least until we're done taking these partial derivatives. So, right, we don't want f in terms of phi and theta, for instance, right? Because if we were to substitute in phi and theta, like what would be these partial derivatives? How would we substitute these things? The answer is we really can't. I mean, you can if you want to make your life extremely more difficult, but I'll just say we can't. It turns out to be a very complicated thing. So for this cross product, again, I'm not going to really, well, maybe I will go through because a lot of things kind of cancel out. For the first component, we have dy of 0 minus dz of x of negative x. So we get a negative dz dx. Or maybe I should write this as del z of x. For the second component, we get a negative out in front. And then we'll have 0 minus del y del z. I'll write this as del z of y. And for the third component, we get del x of negative x minus del y of y. Okay, so all this is to say that we get a 0 in the first component, we get a 0 in the second component, and we have a negative 2 in the third component. But just to kind of show where these go, it's not that like everything was 0 in these before we took partial derivative. It's that, you know, some terms survived, but we needed, when we took the partial derivatives, everything went to 0. Okay, so again, do not substitute your vector field quite yet, because this nabla vector, it's really hard to change in terms of u and v. Okay, so I think we have it all. I think we have everything in order to set up our integral. We have, oops. We have bound 0 to 2 pi, 0 to pi over 2. Right, so we're doing dp d theta in this case. We have our curl vector 0, 0, negative 2. And we're dotting that with our cross product of the partial derivatives vector. And again, forgive me for shortcutting a little bit. Make sure to write it all down correctly. But I'm shortcutting here because when we take this cross or dot product, we take the dot product. These first two products are going to be 0 since we have the 0 there. So it's not that I don't care about those first two entries. It's just that I don't care to write them back out. Anyways, once we get this cross or dot product, we have this integral of -18 sine of phi cosine of phi d phi d theta. Now what's nice here is, well, you can factor out this -18. But here you get a u substitution, right? You can pick u equal to sine or u equal to cosine. It turns out it really doesn't matter. But if you pick u equal to u equal to sine, then du is equal to cosine d phi. So you get a u substitution here. Since this is not on a loop, you can do this as kind of normal. But the point is, everything should actually cancel out to a -18 pi. Right, well, we know that from before. And if you want to go through the problem again, you pick u equal to sine, du equal to cosine d phi. Your bounds change a little bit, and so that's kind of what happens here, right? Your bounds go from 0 to pi over 2 to 0 to 1 for your bounds, right? And then you go through, you do the integration, you get a 1/2 below, that cancels out with this 2, and then you get your pi hanging out. So turns out we actually do get this -18 pi. There's kind of a rough picture of what's going on, but turns out Stokes' theorem, it works. Okay. Are there any questions about Stokes' theorem, about this going on? Again, this is kind of like, this curl vector is new. Again, the idea is don't do anything too hasty. Right, don't plug in your substitutions for your vector field yet until you finish it off. But then when you have this 0, 0, -2, it doesn't, you don't have anything to substitute in at that point. Yeah, so are there any other questions? Any questions about like rest of the semester, anything else? Again, I saw a lot of stuff that was posted in the discussion board. I didn't get a chance to read them. Okay, I'm not seeing anything, so I think for the last 3 minutes, I am going to actually just go through this derivation. I didn't realize what time it was. I realized there wasn't really enough time to do anything else. I think I would have gone through this, but now we will. Okay, so when phi is equal to pi over 2, u is equal to 1, right? Because that's sine of pi over 2. And u is equal to 0. When phi is equal to 0, u is equal to 1, 0. Sorry, I feel like I misspeak a lot more on Mondays than any other day of the week. Maybe it's just Monday. Maybe it's just I still can't write out the letter phi. I don't know. I apologize for that. So hopefully we all get it figured out. So this is 0 to 2 pi, 0 to 1, negative 18u du d theta, zero to 2 pi. We can actually integrate this now. So we have a negative 18 u squared over 2 going from u equals 0 to 1 d theta right. The only thing here that really changes is now we have a negative 9 d theta, but this is actually the exact same integral that we had before for the circulation part. You go through, you calculate it, you get a negative 18 pi. Okay, so for tomorrow, we have 2 more examples for Stokes' theorem. That will probably take up most, if not all, of tomorrow. If anything, we'd only be able to write out the divergence theorem at the end of tomorrow. So we'll have all of that, but then the divergence theorem section is relatively quick. We have basically one example. It's a very long example, but sorry, we have 2 examples. One of them is kind of long. One of them isn't that bad at all. So we will for sure be done on Wednesday, but it will go into Wednesday. So I will see you guys then.